This is very important because much of the cryptography is based upon this. So here is what happens in the mod. Normally what happens without the mod, same thing happens with the mod. X times y is simply x mod y, x mod m times y mod m, mod m. What that means is that if you take two numbers, multiply them together, you don't have to multiply. These could be very big numbers, right? You don't want to multiply the big numbers. So what you do is you take mod of the first number, mod of the second number, multiply them. If the product is more than m, you mod again. Everybody understand this formula? X times y mod m is x mod m times y mod m times, mod m. All right, same thing for plus. X plus y mod m, you can just take the mod and add. So here is an example. Not a very good example actually. But it is, actually this is a good example, not a problem. Here it says 225 plus 285. Just imagine these are very big numbers compared to 187. And you want to add them. What you do is you take the mod of the first one, take the mod of the second one, and you add them, and you get mod of the first one is 38, mod of the second one is 98, you add up 136, which is less than 187. So that's the answer. Okay. So similarly, x minus y is simply mod minus in mod. Power is same thing. If you want to calculate x raised to 4, where x is a big number and 4 could be a big number too, you could have x raised to 4 million, then you don't have to do this. Basically what you do is x square is product is x4, right? So you can do piece in pieces and then do the mod. It doesn't have to be x squared, it could be x cubed times x is also x raised to 4. So somehow you find numbers which are small enough that you can do, and then you can do mod. X raised to ij is same thing. These are also examples of the same multiplication thing. You do x raised to I, find the mod, and then do j, and then find the mod. An example of this is that you want to, well, first let's do example of maybe this one, x raised to 4. Suppose you want to find out 125 squared. So 125 squared is this, and the mod is 104. Now if you want to find out raised to 4 would be big number, so we can do squares times 2 times squares. So we do the 125 squared, and then we squared it again. First time we get 104, we square that, and we get 157. Okay. And if you want to get 6, you just do 4 times 2. 4 is 157. 2 is 104. Multiply those and you get 59. Everybody feels comfortable with that kind of mathematics, arithmetic? Okay. So now just introducing some symbols. Z is the set of all integers from minus infinity to plus infinity. Zn is the set of non-negative integers less than n. So Zn, it goes from 0, 1, 2, 3 to n minus 1. So there are total n members in this set. For example, Z2 would be 0 and 1. Z8 will be 0, 1, 2, 3, 4, 5, 6, 7. Okay. So addition, subtraction, multiplication can all be done in Zn. So all Zn's, you can do that. So basically, for example, 5 plus 7 mod 8, we already know is 5, is 12 is 4, and so on and so forth. 3 by, and here's another instrument, 3 by 7 mod 8. What is 3 by 7 mod 8? You see, so we have to find number that multiplied by 7 gives you 3. Right? When you want to divide, means you want to find out something that you multiply it. So, and here is another thing in the mod arithmetic. Adding 8 or subtracting 8 makes no difference. So for example, we had 12 here, we subtracted 8 and no problem. The number remains the same. Similarly here, you can keep adding 8 until it is divisible by 7. So you added 3 plus 8, 11, doesn't divide. Plus 7, 18, doesn't divide by 7. Plus 7, 8. Am I doing it right so far? 16 plus 3, 21. 19, doesn't divide. 24 plus 3, 27, doesn't divide. 32 plus 3, 35 by 7 divides. Right? So we say, okay, we will add 32 on the top, and that gives me 5. So 3 is same as 35 in mod 8 arithmetic. Right? Because anything which is multiple of 8 doesn't count. So 3 is same as 35, and therefore 35 by 7 is 5. Then 5 star 5, 25 mod 8 is very easy. That's easy. Any question about any of these mod operations? If you can understand division, then you understand everything else. Everybody understood this part? Okay, so there are several ways to do this. One is the one simplest way I told you, that you keep adding 8 until this becomes an integer. So we added in the numerator 8.
Oh, until it divides evenly. Okay.
Yeah, so I added 8, 16, 24, and 32. With 32, it divides evenly.
Okay, yeah, I understand that for that.
Yeah, right. So that is easiest way. Another way is to find the inverse of 7. Now, if you remember that we taught you how to find inverse of a number. So if you find that, and then you can multiply that and all that. So anyway, you will get 5, and we will see many different ways of doing. So division is just the opposite of multiplication. So you could call it, for example, 3 by 7 mod 8 equal to x. Now, we don't know x, but we know that some multiple of 8 plus, x would be multiple of 7. Same thing anyway. I think the easiest thing is to just do by this, adding 8 until you get a clear division with no remainder. All right. So now let's give some names to these things. Commutative. An operation is called commutative if the order doesn't matter. So w plus x is same as x plus w. So the plus operation is commutative. W times x is same as x times w. It's commutative. Can you think of something which is not commutative? We just saw an operation. Division. X upon y is not the same thing as y upon x. So that's not commutative. Associative. Associative requires 3 numbers, and it doesn't really matter which one you do first. So x plus w plus x plus y is same as w plus x plus y. Whether you do the second addition first or the first addition second, something that doesn't matter. Multiplication is also associative. Okay? Now, so these are different properties. So it is not necessary that everything that is commutative will be associative. It's just that we have the same example doesn't mean that they are all universal. Okay? So some operations, as you will see in a minute, are associative. Some operations are commutative. Some are distributive. Distributive means that one operation distributes over other operation. You need 2 operations. So here we have w times x plus y is that you want to multiply. First you want to sum and then you want to multiply. You can do the other way. You can do multiplication first and then sum later. We have distributed the product over the sum. Okay? Identity. Identity means unit. So 0 is the identity for addition. When you add 0, the number doesn't change. And 1 is the identity for multiplication. When you multiply by 1, the number doesn't change. Additive inverse. So anything that produces the number produces 1 after by multiplication will be inverse. So what is inverse of 8? 1 upon 8, because you multiply 8 by 1 upon 8, you get, that is multiplicative inverse, right? Similarly, additive inverse is basically minus. If you add minus w to w, you get a 0. So whatever gives you identity. So we have plus and minus we are using as an example because everybody knows them. Now we will see some very complicated operation. Okay, and on some very special set of numbers. But before I go to the special numbers, set of numbers and special operations, everybody should feel comfortable with these names, at least for multiplication and addition. So you should know what is an identity of addition, what is an identity of multiplication. What is an inverse of addition? What is an inverse of multiplication? What is commutative? What is associative? What is distributive? Distributive requires 2. Associative requires 3 parameters. 3 parameters. Distributive requires 2 operations. Right? So you distinguish between the operations and the parameters. And then the commutative is basically, 1 operation, 2 parameters. All right. So this is all. We already understand this. Any question about this? All right. So now homework 4b. Now this is the homework that you will do at home, not here. You are supposed to calculate 125 raised to 107. You're not supposed to put it in your calculator and say, okay, what's the number? You should really do it on a piece of paper, because this is something can be asked in the exam, and you don't have to remember anything, because basically this is 107, assuming there's a large number. All you have to do is somehow make it power of 2's. So 107 would be 64 plus 64. If you subtract 64, you get 43, right? Then 43 is 32 plus 11, right? And 11 is 8 plus 2 plus 1. So you just make into power of 2's, and then you just calculate. So you can calculate what is 125 squared. Square that, you get 125 raised to 4. Square that, you get 125 raised to 8. Square that, you get 16, 32, and 64. These are all small numbers. All those numbers will be less than 187. Right? Multiply the proper numbers, and you get this number, 107. Everywhere your number would be less than 107. And you can do it on a calculator or on a computer which has less than this number of, basically a very small number of bits. And the same thing now, basically in the cryptography, you are not going to do with 125 or 187. What you're going to do is, number which is this big, power is this big, and then you have to do calculation. Okay? And so the easiest way to do it is to break down into powers and then use the arithmetic. Everybody feels comfortable doing this, or shall I explain more? How to calculate 125 raised to 107? Okay. All right. Then, yeah.
The modular dividing calculation.
Modular division calculation. Okay.
So, for example, if we say 7 divided by 7 mod 8, then what should be the answer?
7 by 7 is 1, mod 8 is 1.
So if there is some calculation we can, so if it's divisible within the bracket, then we just calculate it and mod.
Then just calculate, yes. The thing is, all we are trying to do is make the bracket integer. If it is already an integer, then no more work required.
Okay. So this, the answer 5 is also valid for 11 divided by 7 mod 8.
Yeah. See, here is going to, you made a good observation. Now, 11 is same as 3 in the mod 8 arithmetic.
Okay.
Right? You agree with that? 11 is same as 3 in mod 8. Okay, yeah, go ahead. Next. All right. So now, a little bit more. Groups. A group is a set of elements that is closed with respect to some operation. What is closed means? Closed means that the result is in this set. Okay? So if I define an operation called dot, and it is associative, as associative means A dot B dot C is equal to A dot B, A dot parenthesis B dot C, and then I have an identity, so that if multiplied by some E identity, it remains the same, and if it has an identity, it will have an inverse, so that if I multiply A by A inverse, I get an E. If these conditions are satisfied, so you have to, these are the 4 conditions: closed, associative, identity, and inverse. Those are the 4 conditions for the group. Then we call that set of elements a group. So clearly, Z8 is that number 0 through 7, mod 8. That set is a group with respect to what operation? Anybody can think of what operation will satisfy all these 4 for Z8? We already saw 2 operations. Can you name one? What are the operations can you do on Z8? Addition and multiplication, those are 2 operations. Is Z8 a group with respect to addition? Yeah, because addition is associative, and addition has identity, and addition has an inverse in Z8. Mod 8, right? I mean, you can get the inverse. So it's a group. It is also a group with respect to multiplication, because it is closed with respect to multiplication, and it is associative with multiplication, doesn't matter how you do it, and has identity, which is 1, and has an inverse for every number. So we know, so basically we first introduced you Z8, and then now we are saying that's a group. Similarly, Zn for any n is a group. Now here is the problem with this kind of course, is that this is a mixture of everything. So basically, I mean, there are people who are very interested in math. They will love this stuff. There are people who are very interested in programming. They will love the protocol part or maybe the lab part. And then architecture people who just like to design protocols, who don't like programming or mathematics, they will love some other part. So there are all 3 parts in this. So this is the mathematical part. Please bear with me. And you need all 3 for this cryptography and security. Although in the real world, you probably will not be designing any security protocols. Probably will be just using them. So, hacking will come out more handy than this part, but it still is good to know. All right. So Z8 is a group. Now, if also there is a commutative. So we talked about associative, distributive, commutative. We didn't talk about commutation. Commutation is not required for being a group. But if it is commutative, then we call it an abelian group. So Z8 is an abelian group for addition, and also an abelian group for multiplication, because both of the operations are commutative in Z8. All right. So everybody understand the concept of group? We just gave a name, group. Now, more names. Cyclic group. A cyclic group is a group that is generated by a powers of something. So you take some number and then you just keep taking powers of that. And the group, if you find a group, that would be a cyclic group. So if you take, for example, 0, 1, 2, 4, 8. This has only 5 numbers. And you take the operation, which is mod 12 multiplication. This whole thing is operation. Mod 12 multiplication. You can show that this is a group, which means that it is closed. You multiply any of these two numbers, the answer is in the set. That it is associative, it has an identity, which is 1. And it has inverse, of course. So this is interesting. It is not Z12. Z12 would have 0 through 11, all the numbers, right? But if you just take these 5 numbers, 0, 1, 2, 4, 8, they will satisfy to be a group. Okay? However, the interesting part is that these numbers are all power of 2. 2 raised to 0 is 1, 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, 2 raised to 4 is again 4, 2 raised to 5 is again 8, and so on and so forth. So you can take any powers of 2, they're all in this set. Yeah. When you will ever get a 0? Good question. Yeah. You're right. I think I have to correct the example. I think it is only 4 numbers that we need here. 1, 2, 4, 8. 0 would be required in the mod 12 addition kind of thing, right? Which we didn't talk about. So for mod 12 multiplication, we don't need a 0. Now let's see. Is the power some fixed element? I mean, we could make minus infinity, but I don't think that is what they mean here. And 2 raised to minus infinity is 0, but I think everything that we have said so far is satisfied by 1, 2, 4, 8. Every element is the power of some fixed element. And closed. All right. For what I would do is I would change this and change the set to contain only 4 numbers, 1, 2, 4, 8. Okay. Now, whether this is a cyclic group for addition, I don't know, and I think that would require a lot more work because then you have to see how do you do that. But actually, cyclic group has nothing. Basically, since it is by definition a multiplication, cyclic group is by definition a multiplication because you just do powers. So it has and the number 2 is called the generator. So for that, actually, this is it. We are all set. 1, 2, 4, 8, mod 12 multiplication. Okay. Any other question? Rings. So the ring is a group with 2 operations, and we can call them addition and multiplication. It is abelian with respect to addition, and they are associative. Multiplication and addition are both associative. Multiplication distributes over addition, and it is commutative. Multiplication is commutative. So, okay, let me not go to commutative. So ring is defined by these 4. This should be number 4. By these 4 conditions. Ring is defined by those 4 conditions. If you find a group and you find 2 operations, and we call them addition and multiplication, and if they satisfy like this, that one operation distributes over the other one, and the one is, and both of them are associative, and that it is abelian with respect to one of them, so on and so forth, then it is called a ring. All right? Just like a group, you have a commutative ring, commutative group, you have commutative ring. If the multiplication is commutative, then we call it a commutative ring. And if multiplication has an identity and no 0 divisors, then it is called an integral domain. So basically, integral domain means all the integer numbers. So examples are coming up. Here is an example. Set ABC. with addition and multiplication. So this is how the addition is defined in this set. There are three elements, A, B, and C. When you add A to A, you get A. When you add A to B, you get a B. When you add A to C, you get a C. When you add B and A and so on and so forth, you get B and B, you get an A, B and C. So this is how the addition is defined. Somebody just wrote down those things and said, this is my addition. Similarly, somebody defined the multiplication, and this is my multiplication. So now we have this set with two operations, and the question is this a ring? So what we have to do is we have to verify that these four properties satisfied. Well, first is not really a property. Addition and multiplication already defined. So we see whether it is abelian with respect to addition. So we just verify A plus A is this. The opposite is true as well. A plus B is B. B plus A is B. A plus C is C, and C plus A is C. So you just do all combinations and see how this is satisfied. Then you see whether it is associative. So you need three parameters. So you just take A and BC, and then B and AC, and you take C and AB, and see if it is associative. And then distribution, and you see whether A times B plus C and B times A plus C and C times A plus B, all possible combinations there, and then you see they are all satisfied. If they satisfy, then it is a ring. If any one of these things doesn't satisfy, then it's not a ring. Now this is a real homework, so you have to submit it. So the question right now is, do you understand how you will go about doing this? If you don't understand right now, it's a good time to ask. I mean, there's no penalty for asking. If you don't understand, I can go back and explain one more time. Okay, actually here it turns out, when I'm looking at it, if I call it 0, 1, and 2, and 1 is 2. 0, 1. Okay, so this is not 0, 1, and 2, because 1 and 1 is 2, and I want a 0. So anyway, so it's not that straightforward, but basically you have to do all possible combinations for to satisfy that these three properties are satisfied. All right. Okay, moving on to field. An integral domain when each element has a multiplicative inverse. If it has a multiplicative inverse, then it is a field. So here we didn't talk about inverses. We talk about association and distribution, and then we talk about commutation, and now identity, and now inverse. So they are all very similar. Sorry, where am I going? Page down, page up, 9. Okay, so if there is an inverse, then we call it a field. Now, the next term is finite field. Now, finite field should be clear. It has just finite number of elements, but the name is Galois field. So next time you hear the word Galois field, you know that it is basically a finite field. That means it has all these four properties, three properties plus commutative plus inverse and identity. All right. So Galois field. Now, the reason I had to bring you here to Galois field is because this is where most of the, basically, I mean, I would have stopped right where the cryptography stops, but cryptography begins here. Basically, is that we use Galois fields which are power of a prime number. So in cryptography, we find big prime numbers, and then we take powers of those prime numbers, and then we operate on those numbers. Okay? So if you take p as a prime number, and you take some power n of that, p raised to n, and you somehow find a field so that when you do that operation, the members are in the same set and they have distribution and all that, whatever we said in the list, right? So that will be called Galois field p raised to n. And Galois field p has 0 through p minus 1. Basically, is this just like with arithmetic operation modulo prime p. And you can do addition, subtraction, multiplication, division, etc., etc. So this will be very much similar to what we talked about modulo arithmetic. For example, if I say GF2, GF2 is mod 2 arithmetic, GF8 is mod 8 arithmetic. Now GF8 is basically 2 raised to 3. 2 is a prime number. Right? And therefore GF8 is a Galois field p raised to n. GF6 is not a Galois field because 6 is not a power of prime. Right? Galois field is only defined when you have power of prime. So now let's start. Would you have Galois field 3, 4, 5, 6? No. 7? Yes. 8? Yes. 9? Yes. And so on. So here is GF7. 7 is a prime number, and multiplication is defined exactly as you would think. All right, multiplying by 0 produces 0, multiplying by 1 produces the same number, and so on. So this is basically mod 7 arithmetic right here. Now we are going to make it a little bit more complicated by saying that we don't do multiplication in numbers, we do multiplication in polynomials. It looks complicated, but it isn't. Once you get used to this thing, then you would be able to do that, and you find it very natural. So basically, so you take a polynomial like this, and what we do is we don't really write x. So if you just take out the coefficient, if you just take out an minus 1, a1, and a0, these are all numbers. Right? They become digits. All right. So, for example, when you write 3,437, you could write down 3437. Those are really coefficients of powers of 10. 10 raised to 3 times 3 plus 10 raised to 2 times something, right? So we don't realize in our mind that I'm writing a polynomial here. But that's what you're doing. When you write a number, all you're doing is taking the coefficients and forgetting the base. So here the base is x. So x raised to n, actually, just x is not actually the base, but x is what we represent as the powers of. And so when you see a polynomial like that, you can add, subtract, and multiply polynomials just like you do all the time, and you can find the remainder and the quotients, and you can factorize them. If you cannot find any factor, then that polynomial is a prime. Okay? So this is polynomial arithmetic. And the main thing is that these coefficients and the multiplication and the division that you're going to do, they could be in mod p base. So when you add two numbers, you just do mod p base. And mod p coefficients operation, right? So I will give you an example. So mod 2. In mod 2, Actually, so this is a polynomial x cube plus x square because all the coefficients are in mod 2. Mod 2 has only two numbers, 0s and 1. Right? So you cannot write 2x cube because 2x cube will be wrong, but you can write 0x cube or 1x cube. Actually, 2 is same as 0. Right? So this is one polynomial. This is another polynomial. When you add these two polynomials, what do you get? You get x cube plus how many x squared? 2, which is same as 0. So the x square is gone. All we get, then we get x plus 1. So the sum is x cube plus x plus 1. If you want to multiply these two, how do you do multiplication? Most people, if you did long multiplication, you would take one of them. Maybe we can take this as the multiplier. So we multiply this whole thing by x cube, right? And then write down, and then multiply this whole thing by x square and write it down and then add. Or you can do other way around. You can multiply this thing by x square and then by x and then by 1 and then you add all of that. And you can do either way, it doesn't matter. So basically if you multiply that, let's say x square, you will get x raised to 5 plus x raised to 4. Then you multiply by x, you get x raised to 4 plus x raised to 3. And you write all this up and add up. Now x raised to 4 will cancel out because we already saw it is twice. Everybody can see that? All right. So maybe you can do it right now and see. Can you multiply this, everybody, and see if you can get that on your piece of paper? X cubed plus x squared. Okay, everybody gets x5 plus x square because x4 and x3 cancel out. It's on the board. Okay, so division. How do you do division? Basically, it is somehow you find the quotient and then the remainder, and so you can basically you do just longhand, just like we do the division longhand. You write down the divisor here and write down the number you want to divide, and then you can, for example, if you want to divide x cubed, x5 plus x squared by x cubed squared 0. That you can do that. Alright, so you can do multiplication and division in the polynomial. The main thing is that the coefficients are mod, powers are not. So you can have in mod 2 arithmetic power of 5, although the coefficient only 0 or 1, yeah.
So I wonder why we have x to the power 4 instead of negative x to the power 4.
Why do we, which multiplication or division?
Division.
In the division.
One, we have x5 plus nothing plus x to 2.
Yeah, so this one multiplied with this, right?
Yeah.
So this one will result in x squared times x cubed, which is x5, x times x cubed, which is x4,
Yeah.
x cubed times 1, x4. Is this what you're asking?
Yeah, but x4, okay, so the polynomial above it is has the coefficient 0 for x4. So that's
Yeah.
basically 0 minus x.
Yeah,
x
minus 1 is
two.
same as plus 1.
So I think this should be a minus 1.
Yeah, okay. There are only two numbers, 0 and 1. Okay? Anything else becomes 0 or 1. So 2 will become 0 and minus 1 will become plus 1. Right? So, yeah, that's a good question. We subtracted, why did not minus? Because we only two numbers, 0 and 1. So the coefficients are in mod 2, which is 0s or 1. Minus 1 is equal to plus 1. Everybody should get that, right? Alright. So now you can divide. Arithmetic modulo and irreducible polynomial forms a finite field. So, irreducible polynomial means a polynomial which is prime. Irreducible means prime, right? We said that. So, if you define a mathematics like this, that is a field, that is a Galois field. And then you can use Euclid's algorithm that we learned before to find GCD, greatest common divisor, and inverses. And the inverses, right? Okay. Now this is an example here. This polynomial x cubed plus x plus 1 in Galois field 2 raised to 3. Alright, is irreducible. First of all, you can verify that you cannot factor it. Okay. Now, you can try different factors, write different polynomials. Since these are very small powers, the number of polynomials of this power are very limited. So you can just try that this is irreducible. Now, if you take that for granted that this is irreducible, then we can write down how you will add. Okay. So 0, 0, 0. If you have a polynomial whose coefficients are 0, 0, 0, that polynomial will be 0 times x. X square, sorry, 0 times x square plus 0 times x plus 1, plus 0 times 1. So that would be total 0. You add to 0, you get a 0. But this would be 1, this would be x, and this would be x plus 1, this would be x square, and so on and so forth. So generally when you write down a number, you are really writing down the coefficients. Alright? So this number is same as this column here, this row here. So 110 means x square plus x. Right? 111 means x square plus x plus 1. 101 means x square plus 1 and so on. Alright? Similarly, on this side, the same thing is repeated. Now, when you add these, whether you can add in the numeric space or you can add in the polynomial space. With polynomial space, you get basically the answers, and that is the answer in Galois field 2 raised to 3 for addition. So 7 plus 7, for example, is 0. Now, if you just do 7 plus 7 in mod 8, you will say, wait a minute, 7 plus 7 is 14. It's not 0. Right? But we are not doing mod 8. We are doing Galois field 2 raised to 3. Here, everything is mod 2, but in polynomials. Okay? So, first write down 7 means this polynomial. Add that, and you get a 0. Alright, same thing, multiplication. If you do in the Galois field, you write down as a polynomial, multiply it, just like we did here, and whatever number you get, write down that numerically, and that's the answer. So, how do you do operations in Galois field? First, convert to polynomial, do the operation, convert back to the numeric number if you need to. Okay, so simple question. Everybody understands why 110 is x square plus x? Right? If somebody doesn't understand, right now is a good time to ask. Don't feel that, And this is all kind of, getting a little bit too deep than I would want to, but we have to. As you will see in the next chapter, we have to use AES is all Galois fields. All right. So in Galois field, coefficients are 0 and 1 because sitting is p raised to n. So everything is coefficients are from 0 through p minus 1, which is 0 or 1. And what this n means is that the polynomial size, everything bigger than x raised to n minus 1 actually, x raised to n minus 1 will be reduced to less. So here the maximum power of the polynomials would be x squared because power 3 here. In 2 raised to 3, in 2 raised to 3, the maximum power of the polynomial is x squared. Even when you multiply x squared to x squared, the power comes down. Okay? So let's take a simple example here. We took x squared and we multiplied to x squared. X squared times x squared is x squared plus x. X squared times x squared is yeah. So let me just correct myself and tell you what it is. Is that there is a polynomial there which is called the x cubed plus x plus 1. That's the polynomial that we are modding with. Okay? So that is equal to 0, but everything else has to be, we have to subtract. So when you get x raised to 4, that's a good thing that I did this right here. So I can now explain to you how we come to this answer. So we want to multiply x squared by x squared. Okay, so we get x4, so that's fine. But what is x4? So the thing is, our polynomial is x cubed plus x plus 1, so nothing can be more than x cubed. So we have to divide this by x cubed plus x plus 1. To bring it down, you want to find the remainder. Right? So we do the same thing that we did before, x4 plus x squared plus x. Subtracted, we get x squared plus x plus 0. Okay, this is it. So that's the answer is there. Remainder. X squared plus x. Yeah.
Why is that polynomial x cubed plus x plus 1 the one that you're using for long division?
Yeah, so this whole table is based upon that polynomial. It's a different polynomial, it will be different. Right? And there are many polynomials which are irreducible, which are prime in this 2 to 3. One polynomial, which is this one, right? So everything has to be done with respect to this polynomial.
Yeah, I was just wondering why that polynomial.
Okay, so hold on. If you take another polynomial, you will get a different table.
Okay.
Alright? And I cannot actually verify, but I have a table in my another book, performance analysis book, table of all these irreducible polynomials because they are used in other places. But, for example, I think if you did x cubed plus x squared plus 1, that will be irreducible. I think that is irreducible. Okay, I'm not quite sure. But so this is another polynomial which is irreducible, prime, and you can write a table, it will be different. Right? So I'm glad I did this because the thing is, addition is straightforward. Addition doesn't change the powers. But when you multiply, you get higher powers and you have to bring it down. So now you can verify on yourself that x squared plus x plus 1 times x will result into this. You can do very easily, right? If you take x squared plus x plus 1 multiplied by x, what do you get? X cubed plus x squared plus x. That is more than power of 2. So you subtract this one and you get. So, all right. So let me ask you again. Does everybody feel comfortable reproducing this table somehow? Can you reproduce? If I ask you to reproduce any particular element, you can reproduce, right? And addition was straightforward. So, this multiplication is something that was not straightforward. And that we did that. 420. Okay, so now going back here. So x square plus 1 is 101 base 2. X square is 1112. Addition is good. Multiplication is given here. Then I added this thing last night, actually after the slides were printed. This little red stuff may not be in your slides. Is it in your slides? So basically I wrote this notation here that when you want to multiply 011 to 101, what you do is you left shift it. 101 means you left shift by 1 and then exclusive OR with left shift by 0. So basically this is longhand multiplication. You first multiply by 1, you get that 101. Sorry, 101. Sorry, I'm just multiplying 101 by 011. So this one will result into 101 and then this one will result into 101, which is slightly shifted, right? So this double angle, left angle means shift left. This is the notation. So anyway, so this one will become 1010 and this one will become 101. Exclusive are them and you get 111. Okay. Interestingly enough, in these examples, we did not come into a case where the power goes more than 2. This is 0, 1, 2, 3. This is 3, so we have to subtract the generator. And generator is not given. So this example is somewhat assuming the generator is previous one. Okay, it is assuming the generator is previous one right here. Yeah. So basically, you get a bigger number, and since this is bigger than x square, you have to find the remainder, and that's what we did. So find remainder would be x square, and therefore that will be the answer would be 0100. So if you're basically saying the same thing that we said here, is that you multiply, and if the number becomes more than x square number, then you have to find the mod. So if you take this polynomial and this polynomial, the result would be x square. X plus 1 times x square plus 1 is x square. Okay. So homework 4D. Determining the GCD of the following pairs of polynomials. GCD, greatest common divisor. Now, greatest common divisor, I don't think, it's much easier to just do by longhand, like this. If you want to do with Euclid's method, you can do it, but I find this is much easier to do by the longhand division. Everybody understands how to find GCD? If you never learned before how to do a GCD by division, is that you take smaller number as a divisor, bigger number here, you divide, whatever comes out as a remainder, you take that as a divisor, bring that here, and do that. Everybody knows that method? Right? How to find GCD? So here you have access to 3 polynomial and you have access to 5 polynomial. And so you You will take the smaller polynomial f raised to 3, make it a divisor. Divide that, whatever remainder comes out, you use that as a divisor and so on. Continue until you get a 0. No remainder left. That would be your GCD. Last divisor would be GCD, or you can use, that would be kind of difficult to use the table. So this is going to give you a good practice of division in polynomial. Okay. I'm just going to do one line so that you can understand what we are trying to do. Everybody probably understands, but since we got class so quiet, I'm going to look at some part of it. So it says that x is 5x5 plus 2x4 plus 6x squared plus 9x. Divide by 5, 2n minus 5. 5x cubed plus 2x squared plus minus 5x. Okay? Minus 2. Alright, so what should I write here first? Anybody? X squared. So I get 5. Tell me, keep telling me. And then plus
2x raised to power 4.
2x raised to 4 minus 5.
5x cubed.
Okay, so
Which is separate.
I should just leave this one here. Minus 5x cubed. Yeah?
Minus 2x squared.
Minus 2x squared. Right? Now I subtract. So I get plus 5 x cubed. Right? By the way, let me just say that I said there is no minus number in the polynomial, they have minus number. So don't worry about that. You can say minus 5 equal to plus 6 in 11, mod 11, right? So that is the same thing. So here I mean, if I got minus 5 and I subtract it and I got plus 5. Now 6 minus 2 is 8 x squared. 8x squared plus 9x. Now cube. So what do? Plus 1. And so on. I'm not going to do the rest of it. But basically, you do the division. And if there is a remainder, you bring that here. This one here, 5x cubed here. Plus 2x squared minus 5x minus 2. You take that and whatever the remainder comes out. And then keep doing it until you get a 0. That is how you find out GCD. All right. Now, so a root of a irreducible polynomial then can create generator from root of a irreducible polynomial, then adding exponents of the generator. So basically, you can use if you can find a root, then you can use powers of the root as the members of the group, set, field, whatever. Actually, and so basically that will we already talked about the generator. So G is the generator, and that brings us to the end of the chapter. And so let's see. 7 things we learned. First thing is Euclid's tabular method. So instead of doing long division, we did a thing in the table where we had U and V. And then we defined several things. Group. Group has few things: closure, associativity, identity, and inverse. So anybody remembers what is associativity? What is associativity?
X plus y plus z, then you can share z over.
Yeah. Abelian is commutative. That's all it means. Ring needs two operations, addition and multiplication, and then there were 2 or 3 conditions which I didn't write down here. Fields are commutative rings that have multiplicative identity and inverses, and then if the field is finite and it's generated on p raised to n, then it's a Galois field, and polynomials with coefficients in Galois field form a field. And so I didn't actually clearly explain this part. Maybe you have read in the book. This is basically the thing is there could be a root polynomial, and then as you keep doing square and cube and fourth power of that little polynomial in mod this irreducible polynomial, you will get a number of polynomials. Those will be member of the set. So, for example, remember when we went back to example this one, you see mod 12, you have 0 through 11. If you have 0 through 11, that's clearly a group. But you can find a smaller number of, which is also a group because they are powers of something. So here we took generator 2 and we generated a set with 4 numbers. Similarly, you can do in the polynomial space. You will get a smaller set. If you have a generator, you can keep doing the powers of the generator. So, summary is that everything that you have been doing so far in math, addition, multiplication, they have been generalized. They have been generalized in several respects. First, they have been generalized here with respect to different operations. Okay. Second, with respect to mod. Third, with respect to polynomials. So we try to give you, one by one, although I think it is just too many things one after another. So you really have to very thoroughly read this chapter. And if you have any question, please feel free. Today is Monday, so Wednesday, please come back with questions. And we can go over this again if necessary. Okay. Now, one more thing, the lab is working. We got the problem fixed. The remote lab is working. You can now access our lab remotely. You got the handout? Everybody got the handout? Everybody picked up the handout for the lab 4. And in this lab, what you're supposed to do is you are supposed to crack the password. So we have not told you your password on one machine. And you're just supposed to get the password file from that machine and crack it and then change your password.